Hello and welcome to MT3. In this lecture we'll be looking at solving ordinary differential equations using series solutions, or the method of Frobenius. Now this is going to be just an introduction to the technique. In subsequent recordings we will look at lectures, we will look at more rigorous ways of using these techniques. But here we just want to see what's it like. So let's have a look at a simple ODE. Now this is one you've seen before. So d squared y by dx squared plus y is 0. Now you know how to solve this. I put a how there. If you haven't, if you can't spot immediately how this can be solved, then please review the previous lectures on this topic. But now we're going to try a different method. We're going to try. Get this here. Okay. We're going to try to use a Taylor expansion. Now why? Well, if the solution y is sufficiently differentiable, then we know that we can represent y as through a Taylor series. So let's see if we can, assume that y is written as a Taylor series expanded about x naught. So y as a function of x is the sum n goes to from 0 to infinity, an, these are coefficients we need to find out, times x minus x naught to the n. Now, if we knew what y was, then these coefficients would be the derivatives of y at the point x naught. But we don't know what y is, and this is going to be the stuff we're going to find out. Okay, so that's our ansatz. And I put a couple of pictures here in case you don't know what Brooke Taylor looked like. Well, that's him. He was at Cambridge. And we'll come to Frobenius soon. Now, Frobenius generalized this. What he said was that this is not enough. What you need is to have a function which is slightly different, that y is equal to, again, the sum, n goes from 0 to infinity, an, but x minus x naught is now raised to the power of n plus k, where k could be any, it's a real number, general, a finite real number. And what k lets you do is you can start to represent more general functions for which a Taylor series, functions for which a Taylor series might not be allowed about x is equal to x naught, and these could be functions with a singularity in them. So this is the guy. This is Ferdinand Georg Frobenius, who made this and many other contributions to this field. And once again, you can find out more about the mathematicians behind these techniques on Wikipedia. It's a great resource, and also more generalizations and more ideas how they link with other kinds of techniques. We won't say, I will look at more about Frobenius's technique later. So how does this work? Well, here's the idea. You take your ansatz, so y is now a series, a Taylor expansion, n goes from 0 to infinity, an x to the n. What I've done here is I'm choosing my expansion point x naught to be 0. So there's no x naught in here. And I've chosen a Taylor expansion. That means this k in the Frobenius solution is set to 0. So we have a Taylor expansion. Now we want to use this in the differential equation, y double prime plus y is 0. So we need to know what y double prime is. And that's easy to find because you can differentiate this expression quite trivially. Y prime is equal to the sum an n x to the n minus 1, and y double prime is the sum an n times n minus 1 x to the n minus 2. Now you can see from here that the term n is equal to, so if n is equal to 0, then we don't get a contribution because of the n over here. The first term is just 0, and here if n is 0 or 1, we don't get contributions. Alright, but I'm keeping the sums formally from 0 to infinity in both cases. Okay, now we put those sums, in fact only the second order sum, the second derivative sum, in our ODE. Now our ODE was, let's just remind ourselves, it was y double prime plus y is equal to 0. So we put those sums in there. 0 is equal to the sum n goes from 0 to infinity of an n times n minus 1 x to the n minus 2. That's the first term, that's the y double prime term. And then we have plus the y term, which is simply the starting ansatz, n goes from 0 to infinity an x to the n. I'm going to call these terms a and b. Now what we want to do is to combine these terms, and to combine these terms I need to have the power of x in the two to be the same formally. Now here's what we're going to do. I'm first going to make a change of variables, effectively a change of variables in the first term. I've got an x to the n minus 2 here. If we call n minus 2 to be n prime, that is n is equal to n prime plus 2, and this is exactly what we do when we're doing a change of variables in integration, only here it's a discrete sum. Now what this means then is when n is equal to 0, n prime is minus 2. When n is infinity, n prime is also infinity. So the new sum, again we're here, the new sum is the same sum, the a term, now gets written as the sum over n prime, where n prime goes from minus 2 to infinity. Where we had a n, we replaced, because n is n prime plus 2, we replace it with a of n prime plus 2. Where we had n, we get n prime plus 2. Where we had n minus 1, we get n prime plus 2 minus 1. And then we have x to the n minus 2. Well, guess what? N minus 2 by definition was n prime, so it becomes x to the n prime. And I hope you can now see where we are heading. What we're trying to do is to rewrite this first sum in a way in which we get an x to the n as we have in the second sum. Now you might say, oh, why don't we go the other way around? Why don't we write the second sum in terms, make this one into an x to the n minus 2? We could have done that too. It doesn't matter which way, which sum you manipulate. So let's simplify this. A then is equal to the sum n prime goes from minus 2 to infinity, a of n prime plus 2, then we have an n prime plus 2, n prime plus 1, x to the n prime. Okay, now just put a note here that the fact that you've got these two terms in here, n prime plus 2 and n prime plus 1, it means that when n prime is minus 2, this one is 0, so we have no contribution. When n prime is minus 1, this one is 0. And effectively, it's only when n prime is equal to 0 that the sum actually begins. So it's only when n prime is 0 that we start, and then we start with a of 2. Okay? These two terms don't contribute at all. So what we can then do is write this, this modified version of a as the sum n prime is equal to 0 to infinity, because the first two terms don't contribute, of a n prime plus 2, and the rest is the same as what we had above. Now we make one more observation. N prime is a dummy variable. It is summed over completely. So whether we call it n prime or m or l, it doesn't matter. And what we're going to do is drop the prime. I'm going to replace n prime with n. And what this lets us do is formally then both a and b, here's b, will be sums over n. Okay, so we finally, in our last step, we have a is equal to the sum over n goes from 0 to infinity, a of n plus 2 times n plus 2, n plus 1, x to the n. And now we put this back into our differential starred equation. So we now replace this expression for a with the new one, and that lets us combine the a and b terms to get 0 is equal to a single sum, n goes from 0 to infinity, of a n plus 2 times n plus 2 times n plus 1 plus a n. This comes from the a n comes from the b term, and close brackets, and the whole thing is multiplied by x to the n. Now this needs to hold for all n in the range of applicability of this differential equation, which we haven't specified, but in this case it's from minus infinity to infinity. Now the xn's here are a set of linearly independent functions, and you can show this for a given finite set of x to the n's by using the Wronskian. Okay, so this is a set of linearly independent functions, and what we are saying is that 0 is equal to the sum Cn times xn. Now if this is true for all x in the range of applicability of this particular sum, which is minus infinity to infinity in this case, then the only way this can happen is if the CNs are 0 for all n. In our case, our CNs is this term in the round brackets. This entire thing is the Cn. So for each n, we've got to have an plus 2 times n plus 1 times n plus 2 times n plus 1 plus an is equal to 0 for all n. And this is called a recurrence relation. The reason it's called a recurrence relation is because it relates the coefficient at some larger n value. So in this case it's a of n plus 2. It relates this one to the coefficient at a smaller n value. And if you can start this from somewhere, then you can get the next one, and then you go on like that. We'll see how this works. This is pretty much exactly the same way you have developed a Fibonacci sequence. There, in a Fibonacci sequence, let's remind ourselves, you started off with a1 is equal to 1, and you had a2 is equal to 1, and then you had an plus 2 is equal to an plus 1 plus an. So that this was a recurrence relation that let you write a3 is equal to 2, a4 is equal to a3 plus a2, which is equal to 2 plus 1, which is equal to 3, etc. You went on like that. Here we have a different kind of recurrence relation. And you can write it explicitly now. You can write an plus 2 is equal to minus an divided by n plus 2 times n plus 1. We're going to use this form of the recurrence relation. So we start with the first term, and let's start with a0. That means we put n is equal to 0 on this side. We get a0 here. Now once we don't know what a0 is, but once we start with a0, some value of a0, then we can get a2. Because if I put n is equal to 0 here, then on the left hand side we have a2. That's equal to minus a0 divided by 2 times 1. Or it's minus a0 divided by 2 factorial. Alright, now we have a2. You might say, what about a1? Well, let's keep that for the time being. So a0 has given us a2. Well, a2, if I put n is equal to 2 here, that would give us an a2 on the right hand side. Well, I will get an a4 on the left hand side. So let's see what that is. So a4 is equal to minus a2 divided by 4 times 3. That 4 times 3 comes in from these two factors in the denominator. And that's equal to, well, we know what a2 is. a2 is minus a0 divided by 2 factorial. So this gives us plus a0 divided by 4 times 3 times 2 times 1, which is plus a0 divided by 4 factorial. Now you can go on developing terms like this, and eventually, if you stare at it for long enough, you will realize that there's a general formula. In this case, the general formula says that the even n terms, now if n is even, then I can write n as 2 times m, where m is any integer. So for even n, we can write these terms. Sorry, let's put this down here. So n is equal to 2m. This is the even case, and a of 2m is equal to a0. We'll always have an a0 times minus 1 to the m divided by 2m factorial. Now you can use this formula to check and make sure that the terms you've got are the correct ones. This is the correct formula. So what this means then is that one of the solutions to our differential equation, and I've written it as y of ex, where e is e for even, that's written as the sum over m. Instead of n, I'm using a sum over m, goes from 0 to infinity, and the terms that will appear here are only the even terms. So it's a of 2m, x to the 2m. Once again, you might say, what about the odd terms? Well, if you start from a0, you get only the even terms. So the odd terms in this particular solution will be 0. Right. And then we put in the expression for a2m. That's a0 times this thing. So we bring the a0 out. Then it's a0 times the sum. M goes from 0 to infinity of minus 1 to the m, x to the 2m divided by 2m factorial. And this is the function you know, because if you write it down, It's a naught times 1 minus x squared over 2 factorial plus x to the 4 over 4 factorial, etc. And this is none other than the cosine of x. And you should have expected this, I hope. So we have the even solution is a naught times the cosine of x. But what about the sine solution? Well, I hope you can guess how we get that one. We go back to the recurrence relation. And this time we start with n is equal to 1. So a1 is the first term. If n is equal to 1, we get an a1 over here. And a1 lets us define what a3 is. If you put n is equal to 1, this becomes a3 is equal to minus a1 divided by 1 plus 2. That's 3 times 2. And that's minus a1 divided by 3 factorial. Then you take this a3, put it in the right hand side. That means n is equal to 3, and you get a5 as plus a1 divided by 5 factorial. You go on developing that, stare at it for a while, and then you realize that if n is 2 times m plus 1, that means it's an odd number. So this is the case for odd n. Then we have a of 2m plus 1 is equal to a1. The a1 is always going to be present, times minus 1 to the m divided by 2m plus 1 factorial. And so we get the odd solutions. Y0 of x is equal to the sum over m. We've changed from a sum over n to a sum over m. And we have only the odd powers of x present in here. We know what these coefficients are. They're given by this. And now we have this solution is proportional to a1, and then we have this power series in x. If you write it down, it's a1 times x minus x cubed over 3 factorial plus x to the 5 over 5 factorial, etc. And this is simply a1 times the sine of x. So the general solution then is y is equal to an even solution plus an odd solution. So it's a naught times the cos of x plus a1 times the sine of x. And you should be happy, have all's right with the world, because this is indeed the solution you would get by solving y prime plus y is 0 using any of the methods we have discussed previously. The method I would use here is, it's got constant coefficients, so you can use the method of constant coefficients. Good. Now there's a hint of a problem, or hints of a problem. Let's consider this ordinary differential equation. Y double prime minus 2y divided by z squared is 0. I've used z as the independent variable here. There's a reason for this. You see, differential equations, we normally think of them as being applied, the independent variables are x, y, real. We're dealing with real numbers. But when we're dealing with the convergence of the solutions, we invariably want to think about the differential equation as a where the primary variable is z, where z is a complex number. And when we talk about the convergence of solutions, we have to bring in, keep in mind that our real functions are just one part of a more general case where functions can be on a complex plane. And singularities in the complex plane will affect how our functions behave on the real line. Now these are ideas which will be developed in complex analysis, so I'm going to leave it at this for now. This is just a hint as to where we are heading eventually. So y double prime is equal to 2y plus over z squared. Now if y is continuous, then as z tends to 0, y double prime, the modulus of y double prime, will tend to infinity. So there must be a singularity in the solution at z is equal to 0. And here's the hint. Will this cause a problem? Well, let's see. This is just telling us that something may be going wrong here. So let's rewrite this differential equation as z squared times y double prime minus 2y is equal to 0. And I put a note here, can you solve this? And I hope you recognize that there is a way we have discussed previously. So how do we solve these kinds of equations? I'll give you a clue. It has to do with Euler. Right, so we make the ansatz again, a Taylor expansion. So y of z is equal to this power series in z. Y double prime of z, the same way as before, is this power series in Z, where we now have additionally the terms n times n minus 1, and we've dropped 2 powers of Z here. Insert this into the ODE, and what we get is 0 is equal to Z squared times Y double prime, which is this power series, minus 2 times Y, which is this power series. We can now bring in the Z squared in here, so that makes the power of Z Z to the n over here. It converts Z to the n minus 2 to Z to the n, and now the powers of Z are the same in both terms, so we don't need any changes of variable or anything to combine these two terms. We can combine them as they are, and what we have is a single sum, n goes from 0 to infinity, of a times n minus 1 minus 2 times an, a whole thing multiplied by Z to the n. Now we apply the same idea as before. Since the functions Z to the n are a set of linearly independent functions, therefore the only way for this sum to be 0 for all Z is if the coefficients themselves are 0 for all n. Therefore we have a times, in brackets, n times n minus 1 minus 2, close brackets, that is 0 for all n. Now here's something odd, we have not got a recurrence relation. The only term we have in here is an. I don't relate an to any other an minus 1 or n minus 2 or n plus 1 or n plus 2, it doesn't matter. There's only one a in here, and it's an. So we don't have a recurrence relation. Okay, but that's fine. Let's proceed and let's see what we get. And this thing must be 0 for all n. Now how can it be 0 for all n? Well, either for a given n, either an is 0 or this term in the brackets is 0, right? That's the only way this can be 0 for all n. So for each n, either an is 0 or n times n minus 1 minus 2 is 0. So let's have a look. If I put n is equal to 0, well, 0 times 0 minus 1 minus 2 is minus 2. This is not equal to 0. That means a of 0 is 0. If I put n is equal to 1, that we have 1 times 1 minus 1 minus 2, which is equal to minus 2. Well, that's not 0 either. Therefore, a1 is 0. And you can go on doing that and find out which ones are non-zero. Or what we can do is to say, hey, let's find out when this is 0 for which n, and that will tell us which of the an's is not 0. Alright, so we solve this equation then. We solve, to find out which an's are not 0, we simply solve this equation. It's a quadratic in n, and the solutions are n is equal to 2 or n is equal to minus 1. Now, n is equal to 2 is allowed, because our sum starts from 0 and goes to infinity. So n is equal to 2 is allowed, which means a2 is non-zero. N is equal to minus 1 is not allowed, because our sum starts from n is equal to 0. So this is below 0, that's not allowed. So we have only one solution. I'm calling it y2 of z, which is a2 times z squared. When n is equal to 2, our solution will be z squared. However, if we had allowed the sum to start from n is equal to minus 1, that is, if yz was written as n starts from minus 1 to infinity of this sum, then the second of those solutions would also be allowed. And we would then have another solution. I've called it y of minus 1 is equal to a of minus 1. That's just the constant of z to the minus 1. In this case, our full solution would have been y of z is equal to a2 z squared plus a of minus 1 divided by z. Now this first solution is well behaved, except as z tends to infinity. The second solution is well behaved except that z is equal to 0. And we kind of anticipated that something would happen at 0. Z is equal to 0, and this is the singular solution. So the Taylor expansion gave us the well-behaved solution only. It did not give us the singular solution. And we had to modify the Taylor expansion to get the singular solution. This is what Frobenius lets us do naturally. So before going to the Frobenius solution, let's just once again look at what happened here. We started with what looked like a fairly innocuous ordinary differential equation. We put in the power series solution. We ended up not getting a recurrence relation. Instead, we got a condition such that for each n, either the coefficient an is 0 or this thing is 0. And what we found then is that there are two possible n values for which this is 0, and therefore there would be only two non-zero terms in that power series. All the rest would have 0 coefficients. And what we got was that one of those terms, one of the solutions was n is equal to 2. This was allowed by the Taylor expansion. Therefore, a2 times z squared is an allowed solution. The second of them was n is equal to minus 1. This is not allowed by Taylor expansion, which begins from n is equal to 0. But it could have been allowed if we had generalized the Taylor expansion to start from n is equal to minus 1. And therefore, if we had made this generalization, we would have had two solutions as expected for a second order ODE. And those solutions would have been a2 times z squared plus a minus 1, the coefficient a minus 1 divided by z. One of these solutions is singular. Alright, so Frobenius, as I've said, lets us do this generalization naturally. We start off with a power series expansion as before, the sum, but now we multiply it by a power z to the k. So this term, this z to the k, lets the power series start from any finite power of z. In fact, k could be real, so it could be a real number, it could be anything. And then this is the kind of well-behaved part, and this part could be singular. Now what we're going to do, because we have this first term z to the k, we've introduced one more degree of freedom here, so I'm going to remove one degree of freedom from the sum. I'm going to require now that a naught is not 0. So the sum will begin from n is equal to 0, and that first term a naught is not going to be 0. This is very important. Okay? Now let's see how this proceeds. So let's use this Frobenius technique in that differential equation. I now need to find my second derivative as before. So y double prime of z is equal to this sum, n goes from 0 to infinity of an, and we differentiate twice, so we get an n plus k, brackets, n plus k minus 1, and z to the n plus k minus 2. Put this into our differential equation. And with the same kinds of manipulations as before, we have 0 is equal to z squared times the second derivative minus 2 times the function y. Bring the z squared in. This makes this power of z the same as the one here. So we can bring a common power of z out, and we are left with an brackets n plus k brackets n plus k minus 1 minus 2an, those brackets. Now as before, this entire set of functions z to the n plus k is a set of linearly independent functions. So the only way for this sum to be 0 for all z is if these coefficients are identically 0 for each n. Therefore, an brackets times this term is equal to 0 for all n. You can put that down here, for all n. And again, we have no recurrence relation. There's only an an here. That hasn't changed. All right. Now we know from construction that a naught is not 0. So when we have n is equal to 0, we'll have an a naught here. Then we'll have a 0 here and a 0 here. That a naught is not 0. So the only way for a naught times the remaining terms here to be 0 would be if the terms in the brackets are themselves 0. So when n is equal to 0, we must have 0 plus k, that's the first thing here, times 0 plus k minus 1, the second thing here, minus 2 is 0. In other words, k times k minus 1 minus 2 is 0, or solving that, you get k is equal to 2 or minus 1. And I hope you're not surprised by this. So for all n greater than 0, this thing can never be 0. With these values of k, this will never be 0. Therefore, the only way for an times this term to be 0, since this is not 0 for n greater than 0, the an's have to be 0 for n greater than 0. And this is what I put down here. So then from our ansatz, what we end up with then is that this power series solution times z to the k. In this power series, the only non-zero term is the term for which n is equal to 0, and that gives you a naught, a constant. And then we have a naught times z to the k, and k can be either 2 or minus 1. So we have two solutions. For k is equal to 2, y2 of z is z squared times a naught. For k is equal to minus 1, we get a singular solution, 1 over z. Only n is equal to 0 contributes, and you have to understand why this is the case. If you haven't, go over this recording once more, this part of the recording. There's only n is equal to 0 that contributes. So the general solution then is y of z is c1 times z squared plus c2 times 1 over z. I have changed the a naughts here. I material it as constants. We want to have two independent constants multiplying the two independent solutions. So I've chosen them to be c1 and c2. They are undetermined. We need to figure out what they are. So let's summarize what Frobenius lets us do. Our ansatz in the Frobenius technique is that y of x is a power series times x to the k. The x to the k term will let us describe things that are not describable by a Taylor expansion. And this includes singular terms. K could be a real number, it could be an integer, negative, positive, doesn't matter, but it's finite. And what we have here is that because we've introduced this x to the k, we've introduced a degree of freedom, and we have removed one degree of freedom from the power series expansion. We have enforced the rule that a naught is not 0. So the sum starts from n is equal to 0. This term is always present. This allows singular solutions, but we will see it doesn't always lead to solutions, and sometimes we don't get enough of solutions. This requires a proper analysis of the singularities in the ODEs, and something called Fuchs' theorem. And of course, always more examples help. So this was the introduction to this topic, and I hope I've motivated the ideas introduced by Brooke Taylor and Ferdinand Georg Frobenius, that you can solve ordinary differential equations using a generalization of the Taylor expansion, which is the method of Frobenius. These solutions can be made about any point x0. In practice, we will tend to use x0 as 0 in our examples, but in principle x0 could be anything. And this will give us a very general and powerful way of solving differential equations. But more on this and more on the details, mathematical details, in subsequent recordings. Thanks for watching.